My name is Afshan Lotfi, and I'm trying to make generative jet engines and rocket engines, and specifically the pumps, compressors, and turbines. And I'm later going to try and get to combustion, but right now that's kind of my focus. So let's dive right into it. So the idea right now is it's as simple as just passing in a very simple data structure of exactly a design, for example, for a compressor that you want. Right now, version 1 only supports compressors, but eventually I want to be able to support pumps and turbines and all those sorts of things. So, for example, for the compressor, you just specify I want a compressor. You say, for example, I want it to have this mass flow rate, which is like how much flow is coming into that compressor for that design, and like say like, okay, I want to 4x the pressure from the on the outlet, and pretty much just specify like how fast is this compressor spinning and the inlet Mach number, like all kinds of inlet conditions for temperature, pressure, and like the target efficiency you want. So this is like 87% efficient compressor, and stuff like stages. Maybe you want a 7-stage compressor to have it be more efficient, but also there's like a weight constraint. Yeah, you want to operate on air. You can also operate on different types of fluids in this later version. So yeah, enough talking. Let's kind of jump into a demo. So this is a demo right here that takes in the design that you just saw. So that's what Mark 1 is. And yeah, so this is, for example, it already does all of the delayed calculations and just straight up spits out the CAD, which is really cool. But let's try and look at a cooler example. Let's actually look at an axial shaft. So all you have to do is just run this, and I already ran this example. It takes about 40 seconds, so let's actually look at the result. And the result is something like this, which is really cool. So what you're looking at right here is one stage of the 7, and if I ran the whole thing, it would probably take like a few minutes to get all the parts and calculate everything. But essentially, you have a assembly here, and all of the parts, everything is generated. Everything from the screws to the fasteners around like here to connect each stage together to the literal attachment of the blades. Everything is generated. And these are primarily based on empirical calculations that you'd probably see in various textbooks, but the next step of this is to validate with simulations, which I'll show what I have so far with that. But yeah, this is really cool, and this is an example of the full assembly, for example, of the 7-stage assembly. You put everything together, it looks something like this, and this is the stator assembly. And this is essentially the thing that goes right behind the rotor that guides the flow. So essentially it causes a pressure rise because it's a stationary blade. Yeah, so this is the example of the CAD generation. Now I have 2 more cool things to show you this week. So the second thing I wanted to show you was this library I wrote called PairFlow. And the point of PairFlow is to define shapes of the passages of the actual compressor itself. So, for example, a compressor, it gets smaller and smaller, and you want to be able to define the geometry of that. So I've essentially done that here. This is an example of a nozzle, but you can also do it for diffusers for jet engines. This is a rocket nozzle right here. And running through this example, what it does is it generates the geometry from proportions and from angles that are passed in, and then it generates the mesh and then runs a simulation on that nozzle, and then you can use the results from that nozzle to then optimize and cause a converge towards a higher efficiency for that specific nozzle. So let's kind of run through this example here. So so essentially it generates the geometry, and then here's some inlet conditions that it's this nozzle is expecting. It's doing it with this weird looking gas that I found at 542 Kelvin, operating at about like 9 bars. And yeah, now it's running through the simulation, so it's meshing it, and what meshing means is essentially it breaks that geometry down into a bunch of discrete points that it can then run simulations on. And yeah, so it's running through, and as you can see, it's iterating. And what it's trying to do is it's trying to essentially converge towards a stable point where it can actually say that these results are valid. So it runs it through a bunch of times, and then it averages the best simulation. And yeah, so that's going to take a second. It's taking a little bit of a sec because I'm recording, but I think I already have a run through of this. Yeah, so if you go here, this is essentially the result. So if we take a look at the Mach number, because it's a rocket nozzle, the whole point is for the Mach to get higher, so that's why it's in red. And the goal would be to essentially perturb these control points for the geometry until you get a efficient and target engine nozzle that you want for your assembly. And you can do this for diffusers as well. And essentially you can keep tuning these points until you get something that is optimal. And that's kind of the idea of this project. The idea of this project is to get something that is a starting point, which you can get from traditional textbooks, and then try and perturb it and run through a simulation until you get something that is optimal. So one more example that I want to run through is the same thing, but for blades. So I want to optimize the shapes of the blade and do the same kind of simulation guided method as before. So, so if we go through here, I have another library I wrote called Parafoil, and it does the same exact thing where you can define both the rotor and the stator geometries, and then what it'll do is it'll run through and give you a mesh, which is what this is. And then finally, you can take that mesh and run it through a simulation. So I already have that run for the sake of time. And if you go here, this is the rotor, and this is the stator simulation. And if we display those, let me go ahead and delete that. So this is the rotor, and this is the stator. And reapply. So yeah, this is our simulation for the blades, and it is all defined parametrically as before with splines, and these splines can be perturbed and altered until we get an optimal blade for both the rotor and the stator. And then the result is you get the pressure for each one. So we have the pressures, and exactly as we expect for a turbine is supposed to take in high pressure and it's supposed to become lower pressure, but then the result is that you get energy out that can be, for example, used to turn the shaft. And if that's what you're trying to optimize on, then you can take the results of this and feed it back into an optimizer and then perturb the shapes until you get something that is optimal. And all these tools you're seeing here, even the visualizer, I've written from scratch. Most of the software is thousands of dollars and it's commercial. This is 100% free and open source, and I'm happy to release this to the world free of charge. So anyone watching this, feel free to go to openorion.org and check out all the libraries that are free at your fingertips right now. Thank you so much for your time.